Approximate integration refers to techniques that we use to approximate integrals without actually finding antiderivatives. Recall that when you first saw integration, it was presented as the area under a curve from A to B, such as we have in this diagram. And you were probably told that the area is approximated by the sum as I goes from 1 to n of f of x sub I star times delta x, where this f of x sub I star times delta x refers to the area of a rectangle. I've singled out one rectangle here, and suppose it's got a left endpoint of x sub I minus 1 and a right endpoint of x sub I. And the idea when you first saw this was that x sub I star is just some number in the ith subinterval. You may have computed stuff using the left endpoint of each subinterval, or the right endpoint, or even the midpoint. For now, let's focus on the midpoint. Using the midpoint, instead of x sub I bar, we can call it x sub I, instead of x sub I star, we can call it x sub I bar. And it represents the average of the x values. And so it's x sub I minus 1 plus x sub I divided by 2. And the idea is that the output associated with that particular input gives us the function height. The width that actually gives us an area is referred to as delta x. And it is, of course, x sub I minus x sub I minus 1. You also would have seen that expressed as b minus a divided by n, where n represents the number of subintervals and b and a are the x values of the endpoints. Well, folks, using the midpoint as the input value for the function leads to something that we call the midpoint rule. The midpoint rule says that the integral from a to b of f of x dx is approximated by m sub n. The m represents midpoint, and the sub n is the number of subintervals. And the value is given by delta x times the quantity of f of x sub 1 bar plus f of x sub 2 bar plus plus f of x sub n bar, where delta x is equal to b minus a over n, and x sub I bar is equal to x sub I minus 1 plus x sub I divided by 2, which is the midpoint of the ith subinterval, which is the closed interval from x sub I minus 1 to x sub I. Now you can tell that if we're using midpoints to define our function height for each rectangle, then we're going to be off by a bit, right? I mean, we're a little bit under here, and we're a little bit over here, and we'll have a pretty close approximation. You know, this isn't a pointless endeavor, but there's going to be some error involved. And a numerical analysis yields that for the error, we use the second derivative of f. And if the second derivative of f is less than or equal to some value k for all the x's in the interval from a to b, then the error in the approximation is given by the absolute value of e sub m. Now, e is, of course, error. The sub m means that we're using the midpoint rule. And it's less than or equal to that k that we just looked at times the quantity of b minus a cubed divided by 24n squared. N is the number of subintervals. B minus a, well, that's the width of the interval to begin with, right? The a and b endpoints. As far as k, we'll see more about, I'll show you how to figure out k, but it's a value that the second derivative is never bigger than over the interval in question.